Mars Climate Orbiter existed to study a planet shaped by an atmosphere in constant motion. The spacecraft is often represented in artwork sweeping above Mars, its instruments turned toward the surface, and the thin envelope of gas surrounding it. But this image shows the mission as it was intended to unfold. The real spacecraft would never begin its planned work in Martian orbit. To understand what was lost, it is necessary to look beyond the engineering failure that would later define the mission. Mars Climate Orbiter belonged to a much longer effort to observe a world whose climate changes across seasons, across landscapes, and across immense spans of time. By the 1970s, orbiting spacecraft were already recording those changes. On the 11th of August, 1977, Viking Orbiter 2 photographed the southern polar plains during its 356th orbit of Mars. The image was taken late in the southern summer, when the seasonal polar cap had contracted to its minimum extent. A faint veil of water ice cloud was visible over part of the cap. It was one observation within a regular climate monitoring program, capturing a planet that was not simply cold and static. Frost accumulated and retreated. Clouds formed above the surface. Dust and ice moved through repeating seasonal cycles. Such observations offered individual moments in that cycle. Understanding the larger system required measurements made repeatedly, from orbit, over extended periods. Each image could show what Mars looked like at a particular time. A sustained record could begin to reveal how the atmosphere, surface, frost, and polar deposits interacted. The northern pole preserved a different kind of record. On the 24th of July, 1978, Viking Orbiter 2 observed the North Polar Cap during northern midsummer. Much of the seasonal carbon dioxide frost had already changed directly from solid ice into gas, exposing fine layers of water ice and dust beneath it. Those layers are thought to preserve evidence of Martian climate extending back several million years. They record change on a scale far beyond a single season, periods in which ice and dust accumulated under conditions that were not always the same as those seen today. Mars therefore presented scientists with two connected problems. They needed to observe its atmosphere as it behaved in the present, while also reading the physical traces of climates that had existed in the distant past. An orbiter could return to the same regions, follow seasonal changes, and examine the planet as one interconnected system. By 1998, Mars Climate Orbiter had been prepared to continue that work with a new generation of instruments. Its story would begin with a carefully constructed spacecraft, a complex network of organizations on Earth, and a journey of hundreds of millions of kilometers. The mission would ultimately be lost because parts of that network did not communicate with the precision that interplanetary flight demanded. Mars Climate Orbiter was developed as a dedicated robotic observatory. From orbit, it was intended to examine the Martian atmosphere and support the continuing investigation of the planet's climate. Its design reflected the severe constraints of interplanetary flight. Every instrument, antenna, solar panel, and propulsion component had to fit within a spacecraft compact enough to launch from Earth, yet capable of operating after a journey through deep space. It would also need to navigate accurately enough to enter orbit around another planet. That last requirement involved more than the spacecraft itself. Mars Climate Orbiter depended upon an interconnected system of flight hardware, ground software, navigation calculations, operating procedures, and engineering teams. Information had to pass reliably between every part of that system. A calculation could be mathematically correct within one program and still become dangerous if another program interpreted its output differently. By the 27th of May, 1998, the actual flight spacecraft was undergoing testing. These preparations were designed to establish whether the hardware could survive launch and perform its assigned functions. The testing process addressed the physical machine, its structure, electrical systems, communications equipment, instruments, and moving components. Engineers could examine how the spacecraft responded to simulated operating conditions and verify that individual systems behaved as intended. But successful hardware testing could not, by itself, validate every interaction that would later occur on Earth. Once the mission was in flight, its path would be reconstructed through measurements, mathematical models, and commands generated by different parts of the ground system. The spacecraft and the people controlling it formed one operational chain. Its safety depended upon the interfaces between them as much as upon the reliability of the hardware. On the 13th of November, 1998, Mars Climate Orbiter was photographed awaiting a spin test. The test belonged to the methodical sequence of preparations needed before launch. Nothing in this image indicates a spacecraft approaching failure. The orbiter was real, assembled, and close to departure. The problem that would eventually destroy the mission was not an obvious broken component visible on its exterior. It was embedded in the handling of navigation information, a discrepancy that would matter only after repeated calculations had influenced the estimated flight path. That distinction is central to the accident. A spacecraft may be functioning normally while the model used to determine its position becomes progressively inaccurate. If the difference remains small, it may resemble ordinary navigation uncertainty. If it continues undetected during an interplanetary approach, the consequences can become irreversible. Before departure, the orbiter had to be arranged in its launch configuration. Components intended for use in space were secured within the compact form required for ascent. After separation from its launch vehicle, the spacecraft would adopt its cruise configuration, establish communications, and begin the long sequence of navigation updates leading to Mars. The launch configuration diagram captures the mission at the boundary between preparation and flight. Years of engineering were about to become an operational test of the complete system. Once the spacecraft left Earth, its course could not be treated as a fixed line drawn in advance. Navigators would continually estimate its position and velocity, compare predictions with tracking data, and calculate corrections. Small forces acting on the spacecraft had to be included in those estimates. So did the effects of maneuvers used to control its orientation. Each contribution might be slight. Across months of travel, however, slight differences could accumulate. Mars Climate Orbiter was nearly ready to begin that journey, carrying instruments designed to study another planet. At the same time, the mission was entering a regime in which a misunderstanding measured on Earth could eventually alter where the spacecraft passed above Mars. Mars Climate Orbiter was launched on the 11th of December, 1998. Once the launch vehicle had carried it away from Earth, responsibility shifted from the machinery of ascent to the quieter work of interplanetary operations. The spacecraft now had to cross the distance to Mars while remaining correctly oriented, electrically powered, and in communication with controllers on Earth. Its course would be refined through trajectory correction maneuvers. Between those deliberate changes, smaller forces also had to be accounted for if navigators were to predict precisely where it would arrive. A trajectory diagram makes the journey appear clean and predetermined, an arc leaving Earth, crossing interplanetary space and meeting Mars months later. In practice, that line was continually reconstructed. Tracking observations allowed navigators to estimate the spacecraft's position and velocity. Mathematical models then projected its future path. Whenever the spacecraft used its thrusters, the resulting impulse had to be included in those calculations. This included small firings used to manage the spacecraft's orientation and the momentum stored in its control system. One piece of ground software supplied this impulse information in pound-force seconds, a unit from the United States customary system. The navigation software receiving the data expected Newton seconds, the corresponding metric unit. A pound force is more than 4 times a Newton. The numerical values were passed across the interface without the necessary conversion. The spacecraft itself was not confusing miles with kilometers, and no onboard instrument was choosing between two measurement systems. The discrepancy existed in information exchanged between separate parts of the ground operation. One system produced a number according to one unit convention. Another interpreted the same number according to a different convention. That distinction explains why the mistake was not a single dramatic event. Each affected value represented a relatively small force, but navigation depends upon accumulating such effects over time. When the impulses were interpreted incorrectly, the calculated model did not fully represent how the spacecraft's path was changing. Tracking data still described the spacecraft's motion, and later analysis could adjust the estimated trajectory. Yet the persistent difference between the model and the actual forces complicated that process. The approaching geometry became increasingly important as Mars drew nearer. A small angular error across an interplanetary distance could translate into a large difference at the planet. The incompatible units were therefore the immediate technical error, but not the complete explanation for the loss. An interface requirement should have defined the expected units unambiguously. Verification should have tested whether data retained the same meaning as it moved between systems. Unexpected navigation behavior should have been investigated until its source was understood. The failure involved not only an incorrect number, but the safeguards that did not identify and correct it. All the while, Mars Climate Orbiter carried the instruments for a mission that still appeared achievable. The Mars Color Imager was intended to observe the planet's atmosphere and surface across broad areas. Alongside it, an infrared radiometer was intended to investigate atmospheric conditions. The spacecraft was not supposed to remain immediately in its final scientific orbit. After arrival, it was to use aerobraking, passing repeatedly through the upper atmosphere so that drag would gradually reshape and lower its orbit. That plan made the accuracy of the initial encounter critical. The spacecraft had to pass close enough for orbital insertion and later aerobraking, but not so low that the atmosphere placed it in danger. By September 1999, the cruise was nearing its end. The spacecraft remained in communication, its scientific purpose still intact, but the navigation solution guiding it toward Mars contained a discrepancy that had accumulated across the journey. The mission was approaching the point at which a ground system error would become a physical trajectory, and the margin for recovering from it was rapidly disappearing. On the 23rd of September 1999, Mars Climate Orbiter reached the end of its interplanetary cruise. The spacecraft was scheduled to fire its main engine, slow down and enter orbit around Mars. For controllers on Earth, the decisive events could not be watched directly. Signals required several minutes to cross the distance between the two planets. Every observation described something that had already happened, and the spacecraft had to perform the critical maneuver autonomously. As Mars Climate Orbiter approached the planet, its engine began the planned burn. Soon afterwards, the spacecraft passed behind Mars as viewed from Earth, and its radio signal disappeared. That loss of contact was expected. The planet itself would temporarily block communications. What mattered was what happened next. If the maneuver succeeded, the spacecraft would emerge from behind Mars and transmit again. Ground stations waited for the signal to return. The expected time passed, but nothing was received. Searches continued on the assumption that the spacecraft might have entered an unexpected orbit or switched into a protective operating mode. No signal was recovered. The encounter artwork represents the arrival that had been planned, not an observed view of the loss. No camera recorded the spacecraft's final moments. Investigators instead reconstructed what happened from tracking measurements, navigation records, and the last information transmitted before contact ended. That reconstruction showed that Mars' climate orbiter had approached far below its intended corridor. The disagreement between the modeled thruster impulses and the forces actually applied had biased the estimated trajectory. By the time the spacecraft reached Mars, the difference was no longer a small accounting discrepancy. It had become a dangerously low flight path through the planet's atmosphere. The precise fate of the orbiter was not directly witnessed. The reconstructed trajectory indicated that it probably encountered atmospheric conditions it was not designed to survive. It may have been destroyed by heating and aerodynamic stress, or it may have passed through the atmosphere and escaped into a solar orbit. What was certain was that it did not enter the recoverable orbit required for its mission. The unit mismatch explained the direction of the navigation error, but the inquiry did not treat it as an isolated conversion mistake. During the cruise, navigation results had shown unexpected behavior. The estimated position of the spacecraft required repeated adjustment, and concerns arose about the approach geometry. Opportunities existed to examine the discrepancies more deeply, improve communication between teams, and perform an additional trajectory correction. Those defenses did not work effectively. The units expected at the software interface were not controlled with sufficient clarity. The transferred data were not independently checked in a way that exposed the incompatibility. Navigation concerns did not produce a timely, coordinated response strong enough to protect the spacecraft. A final correction that might have raised the encounter path was not carried out. The loss therefore developed through a chain. One program produced impulse data in pound-force seconds. Another processed those values as Newton seconds. The resulting navigation error accumulated. Warning signs were not resolved. The spacecraft continued toward an approach that was lower than controllers understood. Mars' climate orbiter had crossed interplanetary space and remained operational almost to the moment it reached its destination. Its instruments had survived launch and cruise. Its engine began the arrival maneuver. Yet the mission was lost because the wider system guiding it had allowed the meaning of a number to change, as that number crossed an organizational and technical boundary. The cost was more than the spacecraft itself. Its planned observations of Martian weather, atmospheric structure, dust, water vapor, and seasonal change would not be made. Its intended support for the companion Mars polar lander was also gone, and before the full implications of the orbiter's failure had been absorbed, that second spacecraft was still traveling toward Mars. The loss of Mars' climate orbiter forced investigators to look beyond the incompatible units and examine the system that had allowed the error to survive. The numerical mismatch was straightforward. Understanding why it had not been caught required a broader analysis of requirements, software interfaces, testing, communication, staffing, and mission operations. The inquiry found that responsibility was distributed across teams and organizations without sufficiently effective coordination. Information needed for navigation did not always move with the clarity or urgency demanded by the mission. Procedures intended to identify and resolve anomalies were inadequate or were not followed effectively. Independent checks did not expose the unit discrepancy before the spacecraft reached Mars. This mattered because complex missions are designed with multiple defenses. A single error should be detected by interface specifications, software verification, trajectory analysis, operational review, or an independent examination of unexpected results. Mars Climate Orbiter passed through those layers without the underlying problem being corrected. The failure also exposed the danger of treating an unexplained discrepancy as something that can be managed without first establishing its cause. Navigation solutions were adjusted during the cruise, but adjustment was not the same as understanding. The accumulating effects could be fitted to new tracking data, while the incorrect impulse information continued to enter the process. NASA's response emphasized stronger systems engineering, clearer responsibility, better communication, and more rigorous verification of the measurements exchanged between software systems. The lesson was not that one family of units was inherently unsafe. Either system could have worked if the interface had been defined, followed, and tested consistently. The danger came from allowing the same numerical value to carry different meanings on opposite sides of that interface. Mars science continued despite the loss. Later orbiters examined records that Mars Climate Orbiter had been created to help understand. Radar observations of the northern polar region revealed layers within a vast mass of ice. Alternating deposits of ice and dust preserved evidence of changing conditions across the planet's history, while the surface continued to grow and retreat with the seasons. These observations came from later spacecraft, including Mars Odyssey and Mars Reconnaissance Orbiter. They were not recovered products of the lost mission, nor could they recreate the observations Mars Climate Orbiter would have made at the end of the 1990s. They show instead that the scientific questions survived the spacecraft built to investigate them. The record extended beyond the polar ice. In Becquerel Crater, later observations revealed rhythmic patterns in thick deposits of sedimentary rock. Groups of layers repeated across the exposed terrain, providing evidence that Martian climate had varied in recurring ways over immense periods. Researchers associated these patterns with long-term changes in the orientation and motion of Mars. Variations in the planet's axial tilt could alter environmental conditions and influence how sediment accumulated. The resulting layers became a physical archive, recording cycles far older than any spacecraft. Mars Climate Orbiter had been intended to investigate the present atmosphere, the movement of dust, water vapor, temperature, and weather across the planet. Later missions demonstrated how such present-day processes connect to a much longer climate history. What happens in the atmosphere can eventually leave traces in ice, dust, and stone. The success of later observations should not obscure the consequences of the 1999 failure. Scientific opportunities were delayed or redistributed among other missions. Data expected from Mars Climate Orbiter were never collected. The loss also weakened the paired Mars Surveyor project at a critical moment. Mars Polar Lander reached the planet later in 1999 and was lost during its own arrival. Its failure had a different suspected mechanism and should not be confused with the orbiter's navigation error. Together, however, the two losses prompted a deeper reassessment of NASA's approach to lower-cost planetary missions, including the resources, oversight, and testing required to manage their risks. Mars Reconnaissance Orbiter represented a later generation of spacecraft designed for sustained observation of the planet. Its engineering, communication systems, and scientific payload were different from those of Mars Climate Orbiter, but its development took place in a program shaped by the accumulated experience of earlier successes and failures. No procedure can remove every risk from interplanetary exploration. Spacecraft operate far from immediate human intervention, under severe limits of power, mass, and communication time. That makes disciplined engineering on Earth more important, not less. Requirements must define not merely what information is exchanged, but its units, format, precision, and meaning. Assumptions must be made explicit. Unexpected behavior must be treated as evidence requiring explanation. The Mars Climate Orbiter investigation became an enduring example because the initiating error appears so ordinary. Pounds and newtons are familiar quantities. The arithmetic needed to convert between them is elementary. But the mission demonstrated that simple errors can survive inside complex systems when responsibility for the boundaries between components is unclear. The spacecraft was not lost because interplanetary navigation was impossible. It was lost during an operation humans already knew how to perform. The chain failed because several opportunities to detect, communicate, and correct the discrepancy did not succeed before the final encounter. Later instruments continued to map Mars in increasing detail. The Compact Reconnaissance Imaging Spectrometer for Mars, carried by Mars Reconnaissance Orbiter, examined the surface through reflected light at many wavelengths. Its observations helped identify minerals and locations associated with the planet's environmental history, extending the search for evidence of water and past climate conditions. These results belong to a later mission. They cannot show exactly what Mars Climate Orbiter would have discovered, and they do not replace the missing record from 1999. They demonstrate why orbital observation remained valuable. Each successful mission added measurements that could be compared across terrain, seasons, and time. Mars Climate Orbiter never returned the global climate survey planned for it. Its legacy became inseparable from the way it was lost. Yet describing the accident as a failure to convert units captures only the first link in the chain. The deeper lesson concerns how complex organizations preserve meaning. A measurement is useful only when everyone receiving it understands the same quantity. A warning protects a mission only when it reaches people able to evaluate and act upon it. A safeguard exists only if it is tested under the conditions in which it must work. In September 1999, a functioning spacecraft arrived at Mars, while the system on Earth held an inaccurate understanding of its path. The distance between those two realities was built from small impulses, incompatible assumptions, and missed opportunities. By the time that distance became undeniable, Mars Climate Orbiter had already disappeared behind the planet and would never be heard from again.